because these have been going on for last 1 year. There are some really interesting presentations which are on the past fellowship website. So I would encourage all the students to try to go and attend these talks on the website if they don't have attended in person. So let's start. I'll let Sadie to start her recording.
Started.
Perfect. So thanks very much, Franz, for taking out the time to give a talk today. We're very excited to have you here. And just as an introduction to everyone in the audience, so this talk is part of National Science Foundation PAC Fellowship Program. This fellowship program provides funding for US students to visit the University of Kiel and conduct research up to a period of 1 semester. So the fellowship provides all the support to the students required to travel, to stay in Kiel, to attend different kinds of labs, pay for the materials and supplies, and also take care of all the paperwork involved in their travel. So it's a great opportunity. If you are interested in this fellowship program, please reach out to Sadie Spicer. She's on the call and you probably received email from her, and she'll be able to provide you more details and get you connected with the folks in the program. And Franz has been one of the hosts for our students at the University of Kiel, and we were lucky to have such great mentors in this program. And I know Franz through a program we did together with DARPA, which was on magnetoelectric sensors in collaboration with Eckerd. And I had the chance to actually visit his lab and university several times. And the quality of work at Kiel and in his lab is just phenomenal. There are many areas which are being explored in addition to magnetic field and magnetic sensors. And today's talk, which will discuss about different kinds of nanocomposites and organic films. But as you will see, that this is state of the art, and this is probably the cutting edge science in these areas in which Franz operates. So I'm very excited that he is able to present to you today and share his ideas and share his thoughts with all of you. And hopefully some of you will have a chance to visit his lab and stay there. So with that, I'll pass it on to you, Franz.
Thank you very much, Shashank, for the nice introduction. Let me share my screen. Okay, you can see my screen now and also my pointer, yeah?
Yep.
Okay, so the title of my talk was already mentioned, Functional Nanocomposites and Organic Thin Films Tailored on the Nanoscale via Vapor Phase Deposition. Yeah, in my group in Kiel, we are focusing mainly on functional nanocomposites. This is at least our main activity. And we have two types of composites, particulate-based composites and multi-layer structures. The majority of work is carried out in the field of particulate-based nanocomposites. Yeah, we prepare the nanoparticles in different ways. Today, the focus will be on nanoparticles generated in a gas aggregation cluster source, which gives us very good control of the nanostructure. And for the matrix, we use several techniques. For ceramic materials, for instance, we use magnetron sputtering and others. But today, I will focus primarily on initiated chemical vapor deposition, which we use for functional organic films, including stimuli-sensitive matrices and films. And from the different applications which we investigate today, I would like to focus on photocatalysis, plasmonic metamaterials, controlled drug release, memristive devices for neuromorphic computing, and I also will say a little bit about sensors, both gas sensors, but also physical sensors for magnetic fields, for instance. Yeah, let me start with particulate nanocomposites. So composites I'm talking of typically consist of metallic particles in a dielectric matrix. The dielectric matrix could be a polymer, could be a ceramic, and could be also more complex. Yeah, and in such dielectric matrices, we embed mostly metallic, but also oxide nanoparticles. And they can be quite complex. Here, for instance, it's a ternary alloy. And so there are several things we have to tailor to make these nanocomposites function. In particular, we need control over the filling factor, and we go very close to the percolation threshold so that mostly tunneling processes and interactions on the nano range come into play. That's in fact very important. So we are close to the critical point where critical phenomena occur and close to percolation. Yeah, in addition to tailoring the filling factor, sometimes you also need gradients. I will show you examples. And not only do we have to tailor the gaps here on the nanoscale, we also have to control the alloy composition of the particles. And this will be done among other techniques with this gas aggregation cluster source, which I show you in a moment. And also we need control over particle size, at least averaged over a large ensemble. And different from most approaches, we are not so much interested in monodispersed particles. We, by intention, strive for a broad particle size distribution. This allows us to have a very dense packing of these disordered nanoparticles, and then we can take optimum advantage of processes occurring on the nanoscale, so particularly quantum mechanical processes, plasmonic effects, etc. Yeah. Over the years, we applied several preparation techniques for the nanocomposites. The simple approach we were mostly using was to have two sources for vapor phase deposition, one source for the matrix component. This could be, as I mentioned already, sputtering for ceramic materials. Recently, and this will be the focus today, initiated chemical vapor deposition for organic materials. And for the metallic component, we also use conventional deposition techniques like magnetron sputtering or evaporation. But recently, we focus on cluster sources, which allow us to independently control filling factor and particle size. So let me now say a few words about tailoring of such nanoparticles in these gas aggregation cluster sources. The principle is quite old. It was developed by Haberland already many years ago. And the idea is to have a normal magnetron, which you also use in magnetron sputtering, and then you sputter off atoms into the gas phase. And in order to form clusters, we have a high pressure of inert argon or other gases. And then due to the high gas pressure, we have many collision processes between the metallic particles and the gas atoms. And this allows nucleation of metal particles. And then we have an aperture here, orifice, and the particles are deposited into an ultra-high vacuum on the sample. That is our typical approach, which, as I mentioned, allows independent control of particle size and filling factor. We can also avoid reactions because we form the particles in an inert gas atmosphere. And we can also tune the gas sources to have quite high deposition rates up to micron per minute. So that's also interesting for applications. In order to tailor the particles, we need in situ capability to monitor the growth of the particles. This we do, among other techniques, by UV-vis spectroscopy. Here's a typical examples of silver and gold lines, which give us information on the amount of species in the gas phase. But we are also able to observe in situ the growth of the particles, for instance, by observing the evolution of a plasmonic peak, which is particularly interesting for alloy particles. In order to tailor particles, you need not only monitoring, you also need in situ control. But before I come to in situ control, a few words also about monitoring. in a more basic approach, we work with Holger Kersten on in situ laser scattering, and we also work with a group in Daisy and Charles University on X-ray scattering at the synchrotron. So there we get a very important clues on how these particles form and how we can use this to tailor the nanostructure. We just published an article on the phenomenon in plasma polymer and processes, plasma processes and polymers. If you are interested here, we also give a few more details. Yeah, as I said, not only monitoring is important, you also need control. And one way to get in situ control is to use composite targets. So here, for instance, we have a alloy. In order to produce silver gold alloys, we use, for instance, a silver target, and here we have a ring of gold within the target, and then we vary the region of the erosion zone, and this can be done, for instance, by varying the pressure. Recently, we also have an approach where we vary the location of the magnetic field, and then we can in situ determine the ratio of sputtered silver to gold, and this allows us in situ to produce different alloy compositions. We can also, during the deposition process, change the alloy concentration, prepare gradients, etc. Yeah, so with those tools, we are really able to make all kinds of nanoparticles. Today, I will focus on nanocomposites, so nanoparticles in a matrix, but I would like to briefly mention we also use these nanoparticles as such in various applications. We work, for instance, with Rainer Adelung from Kiel University and another partner, Oleg Lupan from the University of Moldavia, on gas sensors. So here we take white semiconductor sensors, zinc oxide based, for instance, and then we decorate them with core shell or alloy nanoparticles to strongly increase the selectivity and sensitivity towards volatile organic compounds, or also as hydrogen sensors. Here's another example of such nanoparticles. In this case, these are aluminum nanoparticles, which we produce by such a cluster source, and they are very interesting for UV plasmonics. Most of you probably know that you have collective excitations of the conduction electrons in such nanoparticle surface plasmon resonances, and usually you explore such surface plasmon resonances in the visible range. Here we focus on UV plasmonics, and we can tailor the resonance frequency over a wide range by tailoring our nanoparticles. A typical application is absorbers, broadband absorbers for ultraviolet applications, for instance. Yeah, before I come to the nanocomposites, a few more words now on, I covered the nanoparticle component. Now I come to the matrix component. And I mentioned we have activities with ceramic matrices also, but today I want to focus on organic films made via initiated chemical vapor deposition. So this is a very nice way to prepare functional organic films and also stimuli sensitive films. And first, I would like to introduce the technique. Initiated chemical vapor deposition was developed at MIT by Karen Gleason some years ago. We established a strong cooperation with the group, and people from Kiel were at MIT, and so we now closely work with Karen Gleason. We learned a lot from her on the technique. So it's essentially free radical polymerization in the gas phase. I think the students are familiar with free radical polymerization to prepare polymers. You have monomers, schematically shown here. And these monomers have unsaturated bonds. And then you take initiators. Initiators are molecules which have, for instance, a peroxide bond, which can easily be broken at mild temperatures. And here in the gas phase, we use hot filaments to break up these initiators to form radicals. And then, like in the wet chemical technique, the radicals interact with the unsaturated bonds in the monomers, and then you form an organic film. This is a solventless technique. You have much more opportunities compared to wet chemistry. You can get a conformal growth. You can do the process at low substrate temperatures. That's particularly interesting. And you have very precise control over the thickness of the films and other parameters. Let me show you one typical example. We use the initiated chemical vapor deposition technique to produce thin film electrets. Electrets are permanent, are similar to permanent magnets. Here you have permanent charges in a material. For developing electrets, you need materials with a very high breakdown strength. And here's a typical example of a Teflon film. This is bulk Teflon, and this is iCVD deposited Teflon. Different from other techniques to deposit organic thin films, iCVD allows you to completely preserve the chemical structure. So here in this Raman spectrum, you see all the peaks of the bulk material also in the thin film. And compared to bulk materials, these iCVD deposited materials have an extremely low defect density. The breakdown strength is about a factor of 10 larger than for bulk materials. And so here's a typical example of such a Teflon film. And to make electrets, we charge those films up in a corona discharge and incorporate permanent charges. Electrets are very important in MEMS technology, in electret microphones and many other fields. And our thin film electrets, which are particularly interesting for MEMS, they have a much higher charge stability compared to commercial films shown here. I will not go into details. We develop such electrets not only by trial and error. Recently, Stefan Schröder from our group, who runs the electret group, he also carries out density functional calculations to get information on the trap depths of the materials and to tailor them through theoretical design. In addition to those electret materials, we use the iCVD films also for surface coatings, functional surface coatings. One recent example are superhydrophobic coatings. This is not so special. Many people develop superhydrophobic coatings. Our coatings were designed for extreme stability towards high pressure. So these are 3D superhydrophobic materials where we use the conformal deposition in iCVD to coat porous materials and to get these 3D materials with extreme stability of the Cassie state in 3 dimensions. We recently, together with Rainer Adelung from Kiel University, also coated his zinc oxide structures. He has zinc oxide network structures. I think many people know his work. And we again make a conformal coating of those structures. And then we etch away the zinc oxide and we get aero hydrogel networks. So these are completely organic hydrogel networks with very interesting applications in biology as scaffolds, for instance. But today I have no time to go into details. Another approach which we are very excited of recently is to make gradient layers with this iCVD technique. Like for wet chemistry, you can make copolymers of 2 monomers, but here we can, during deposition, vary the gradient from monomer A to monomer B. So we can go all the way, for instance, from a hydrophilic to a hydrophobic surface. We can vary physical properties. And we recently demonstrated in a cover story in Materials Today that we also have control on the nanoscale. Yeah. Here's one example where we used a monomer which attaches to the native oxide of silicon, and this makes available the technique for the semiconductor industry. If you can make such films with a very good covalent bonding to silicon wafers, this is a real important requirement for microelectronics application. And then we can tailor within a few nanometer to make any functionality on top. And we get this precision on the nanoscale without going into detail because we have combined the iCVD technique with mass spectrometry. and so we have good in situ control during deposition. Another approach which we pursue is that we try to implement other functionalities into the organic thin films. We work with Rainer Herges from the chemistry department, and he synthesizes for us photoswitchable molecules like azobenzenes or others. And those photoswitchable molecules can reversibly change their state and also physical properties like dipole moment and other properties. And we co-deposit those molecules together with the monomers. Here's an example without going into details. And so we can get photoswitchable ability, so we can reversibly switch between two states. This is interesting for photoswitchable actuators, but also for controlled drug release, for instance. Okay, now I have covered the synthesis of the nanoparticles. I have covered the matrix. I focused here today mostly on organic matrices. Now I would like to show some applications, and I start with photocatalysis and plasmonic metamaterials. I think most of you are familiar with photocatalysis. Photocatalysis is usually based on using wide bandgap semiconductors. The workhorse is titania. You excite via UV light electrons into the conduction band. You create electron hole pairs, and these are very reactive. The electrons and holes lead to formation of reactive species on the surface, and this can be used for self-cleaning and air or water purification, for instance, and other applications. Our specialty is not to make this particle-based, but to develop sputter processes where we deposit highly photoactive titania and other films. Here's an example of normal titania where we manage to get a large effective surface for very active photocatalysis. And we combine this with our UV plasmonic approach, which I mentioned earlier. So we decorated the surface. This is a sketch here, and this is a real TM image. We decorated the surface with nanoparticles of alumina, which are plasmonically active. And so we use the plasmonic enhancement to enhance the photocatalytic activity. We can simply test the activity by using test substances like methylene blue. And what you see here, this is a pristine titania, and this is a plasmonically enhanced titania where the decomposition occurs much faster. In our recent activities on photocatalysis, we do not only use plasmon-enhanced photocatalysis, we also use metallic nanoparticles, which in principle also exhibit plasmonic properties. But here we take advantage of simply charge transfer, which is also very effective in enhancing the photocatalytic activity. So you prevent recombination by trapping the electrons at nanoparticles. More details are given in this recent publication. And we also went a step further. Instead of only using metallic trapping centers, we use hybrid oxide structures. For instance, we use titania in a columnar structure, especially designed for high photocatalytic activity. And then we deposit with the techniques I explained earlier, for instance, Ser oxide or other oxides. And these tiny spots here in this sketch are the cerium oxide particles. Here again, we take advantage of charge transfer, but in addition to charge transfer, we can prepare the particles to tailor the defect structure. So cerium 3+ and cerium 4+ defects here play a key role in enhancing, in addition to charge separation, the properties. And those coatings have excellent self-cleaning properties. We use photocatalysis not only for cleaning and other applications, we also use photocatalysis for photocatalytic deposition. So here we start with a metallic solution. For instance, in case of gold, we use chloroauric acid solution, and then we photocatalytically reduce gold atoms from the solution, and we form metallic nanostructures on the surface. They have excellent adhesion, and by tailoring the reduction conditions, by tailoring the type of solvent and other conditions, we are able to also control the shape of the particles. So we can easily prepare spherical particles, but we can also tailor the conditions such that you get, for instance, such needle-like structures, which are particularly interesting for catalysis and other applications. And since this is photocatalytically controlled, we have patterning ability. So we can use a laser or other light sources or masks to provide patterns. Yeah, I briefly mentioned plasmonic properties, and what I showed you before were particle-based plasmons. So you have collective oscillations of the electrons, of the conduction electrons at the surface of nanoparticles. These are particle surface plasmons. You can also explore surface plasmons on the surface of a metallic thin film, either in contact with air or with a dielectric. Here you get so-called propagating surface plasmons. I think you know this maybe from your textbooks. And those propagating surface plasmons you cannot excite directly by shining light on. You need a plasmonic coupler. This is due to K-matching, and so typically one uses a prism to excite such surface plasmons on the surface of metallic films. And the example I've chosen here is a silver film. And what we want to do here is we want to reversibly switch plasmon-exciton coupling. So we are interested, well, the final aim is all optical switching here. And what we are interested in to switch the resonance frequency of the propagating surface plasmon by using photoswitchable molecules and by coupling the exciton process in these chromophores, which is reversible and can be photoswitched, by couple this with the plasmon resonance. Here, the basic idea is what you know from textbooks. If you have harmonic oscillators, so if you say you have two spring pendula which have different resonance frequencies, which have the same resonance frequencies, so they oscillate at the same resonance frequency, and then you increase the coupling between the spring pendula, and at a certain coupling strength you go into the regime of the so-called strong coupling, and then instead of observing the resonance frequency of the oscillators, you get a splitting. So physicists call this Rabi splitting. And this means that the resonance frequency of the individual oscillators splits into separate resonance frequencies. And our idea is to use this, as I said, for all optical switching by using such photoswitchable chromophores. And the chromophores which we used here, SPO, they can be switched from a state where this ring is closed to an open state. And this can be done reversibly with UV light, and back switching occurs with visible light. And what you see here is the dispersion relation of these propagating surface plasmons for silver, which was recorded by spectroscopic ellipsometry. And now you see if we incorporate these chromophores into a polystyrene film, which we put on top of the silver, then we get this coupling between the surface plasmons and these chromophores. And due to this exciton plasmon coupling, if the frequency matches, then we get a splitting like the two spring pendula, which upon strong coupling split into different resonance frequencies. We did also theoretical investigations of this process. We got a very good agreement between theory and experiment, and we were able to really demonstrate that this is due to exciton plasmon coupling. And we were also able to tailor the amount of splitting by tailoring the light intensity or the content of these chromophores. Okay, I mentioned that I would like to show different applications. Now I come to the memristive devices. I find that this is a very exciting recent field worldwide. People are interested in mimicking the behavior of the neural of our human brain and to develop devices on a hardware basis which emulate neural human brain behavior. And I think from your biology lessons, you know that synapses which connect different neurons change their conductivity depending on how much spikes go through the synapse. So essentially, if you look at this connection between the neurons, you have a connection where the resistivity of the connection increases with the number of spikes going through the connection. And such a, if you want to build something like this, such a synapse in hardware, this is also called memristor. It's a combination of resistor and memory. So we are looking for a device which remembers how much charge flows through the device and which decreases its resistivity the more pulses or charges flow through the device. And already Yo et al. In 2010 published a paper where they showed that such nanocomposites can be very interesting materials for memristive devices. What you need is you need a combination of electron flow and irreversible structural changes. In order to have memory, when electrons flow through the material, you have to make structural changes. And for applications, these have to be reversible. And the idea, which was already pursued by Yo et al., is to combine ion movement and electron transport. So one has a device which is made up of two electrodes. In this device, you have you have a nanocomposite. In this case, it was silver particles in a silicon matrix. And the electrons tunnel from one electrode to the other, and it can go in both directions. At the high fields between the nanoparticles, ions are released from silver. The ions move into the gap here, and the more current flows, the more silver nucleates in the gap, and this gradually decreases the resistivity. And if you switch the electrical field off, you have a memory. And if you take the reverse polarization, you can dissolve the silver again. And so you have a reversible change in resistivity. Yeah. In biology, you need such type of memristors, which we also investigate in our group. But what is also very exciting, you also need threshold-based behavior. So our synapse don't transmit spikes from one neuron to the other if they are below a certain threshold. So you also need such so-called diffusive memristive devices, which go from a low resistive state to a, from a high resistive state to a low resistive state at a certain threshold. It should be below 1 volt in these devices. And then if you go back with the electrical field, at a second threshold, they should switch back. And this is something which we were recently investigating in more detail based on very old work of our group. Already in 2008, we noticed that in our nanocomposites, we form such channels of highly conductive regions because of the huge electrical field between the particles. Ions are released, for instance, from silver particles, and they nucleate on the opposite side, and this leads to the formation of conducting channels. They can also be dissolved again by Joule heating or driven by the high surface energy of the channels. And based on such approaches, well, at that time we had no idea about memristive devices. This came later. But using now alloy particles, where we can tailor the amount of ions that can be released, we can tailor the behavior of such memristive switching devices. Recently, together with Rainer Adelung in Kiel, we combine the approach of memristive devices with sensors. In the beginning, I mentioned that we have sensors for various applications, and by combining those sensors with memristive devices, we can build devices which are called MEM sensors, which mimics the behavior of adaptation in for instance, in the human nose or in the eyes, and there are many other examples of adaptation in biology. And since a couple of weeks, we got a huge grant in Kiel from the German Science Foundation. We work together with people also outside Kiel. It's called Neurotronics. Our speaker is Hermann Kohlstedt from Electrical Engineering, Bio-Inspired Information Pathways. And in this collaborative research center, we explore the behavior of such hardware devices which mimic the brain. And here, nanoparticle networks play a crucial role. We have some ongoing activities that you can also mimic self-organized criticality in dynamic networks. This is a very important requirement for the function of our human brain. And we have recently shown together with colleagues also from New Zealand that such nanoparticle networks exhibit self-organized critical behavior. I have no time to go into this. This is ongoing work, but I think this field of neuromorphic devices is really a very exciting new field where, based on this collaborative research center, I hope Kiel can also make some contributions. Yeah, I said that the main focus of my group is on these particulate nanocomposites, but I want to say at least a few words also on multi-layer structures. And I think from other talks, also from Kiel, but also from Shashanks and other groups, you are familiar with multiferroics, with composite multiferroics. And one activity which we pursue in Kiel are layered magnetoelectric structures. And in Kiel, we are particularly interested in AC magnetic field sensors. We have a collaborative research center. Our speaker is Eckhard Quandt, which many of you here know. And one idea here is to take magnetostrictive layers, which change their shape in a magnetic field, and then mechanically coupling them to piezoelectric layers. And in piezoelectric layers, strain is transformed into a voltage. So by such an approach, you can measure a voltage, AC voltage, if you apply an AC magnetic field. And this can be used for measuring magnetic fields, very small magnetic fields. In particular, you can take a cantilever approach and make use of the resonance frequency. In my own group some years ago, we achieved 3 picotesla per square root hertz at 100 hertz. 3 picotesla is about 1 millionth of the Earth's magnetic field. However, those cantilever sensors operated in the classical way always have a very small bandwidth because you take advantage of the resonance frequency. Some years ago, we introduced a different approach, so-called delta E sensors, where we also take advantage of a resonance, but a resonance occurring at high frequencies. And then we take advantage of the change in Young's modulus in the magnetic field. And this is something we are currently focusing on in this collaborative research subject, among other subjects. We recently got a very good theoretical understanding also of these devices. Here's a recent publication for those who are interested. Yeah. Those magnetoelectric sensors will not be the focus of my talk today, and I also have to come to an end soon. But one point I want to mention, it's a recent development, which is based also on what I told you before. We think about alternative material concepts for those sensors. And here again, we work with Rainer Adelung from our university. And here the idea is to replace the piezoelectric layer by an electric layer. I told you we have these new opportunities to deposit electret films with very good properties. and also as thin films, so it's suitable for MEMS. And so recently we published an approach, details are given here, where we have what we call nano generators for efficient magnetic field sensing. We still have a magnetic material. Also recently in a unpublished approach, we also aim to replace the magnetic material, the magnetorestrictive material, by an alternative concept, which is based on magnetic nanoparticles in a soft matrix. And then instead of a piezoelectric material, we use our electrets. And these electrets induce charges in the vibrating cantilever. And the idea here is to tailor the harmonic potential. As everybody know, if you have a cantilever, you bend it down, you get a restoring force, and this restoring force is linear, which gives rise to a harmonic potential. This is a simple harmonic oscillator every student knows. But now, due to the attraction between the charges, we can compensate the restoring force. And this makes this potential flatter and flatter. So we can make very soft potentials, not by using soft materials. We can even use quite hard materials, but simply by compensating the restoring force via electrets. And this is an exciting new approach, which we currently explore for sensing and other applications. Okay, and with this, I should come to an end. I hope I could show you that nanocomposites have quite interesting functional properties in many fields, optical, electronic, magnetic, etc. We also have bio applications. I didn't say much about drug release, but also in drug release, particularly these iCVD hydrogel layers are also interesting. Yeah. In order to tailor those composites on the nanoscale, you get excellent control by using vapor phase deposition techniques. So wet chemical techniques are not so suitable here, or I should even say unsuitable. You don't get this amount of tailoring. And I showed you one approach based on gas aggregation cluster sources. And for the matrix, we have iCVD. We also use other techniques, but this is what I found most interesting here for this talk. And then I gave you various examples of applications. And I also briefly touched layered structures. Yeah, you can find more work on our website and also on Google Scholar. If you want to get PDFs, just approach me. And before I close, last foil for today, I should acknowledge the contributions of my group. We have a very strong group recently with young investigators. Alexander Wahl, who is in charge of our nanoparticle activities and also of the memristive devices. Stefan Schröder, who works on iCVD. And Sali Vesiroglu, who is in charge of our photocatalysis activities. And in addition to the young scientists, and I think you will in the future hear much more from them, we also have senior scientist Cenk Aktaş, who partially works with us and partially in Turkey, and Thomas Strunzkus, who works with us since a long time. I should also mention Klaus Retzke, but he's in a different field. And maybe the most important member of our group is our engineer, Stefan Reders, because he designs all the machines we are using. And then in the recent work, I presented various PhD students who are involved. And finally, I would like to acknowledge funding. We have a lot of funding, but mostly by the German Science Foundation. And we have 2 collaborative research centers in Kiel and the Integrated Research Training School. Yeah, thank you very much for your attention.
Thank you very much, Franz, for this amazing talk. It's a lot of exciting stuff. So,
thank you.
So, folks, if you want to ask question, you can just raise your hand. There's a button called reactions.
Yeah.
You could just type your question in the chat, and I can ask.
Yeah. I have the problem because I have my foils on the screen. I don't see many people. So maybe if you have questions, you just ask, or Shashank can read them from the chat, maybe.
Hey, George, why don't you go ahead and ask a question? Yeah.
Hello, can you hear me?
Yes.
Hey, Dr. Faupel. Fascinating talk.
Sure. Good to see you again. Yeah.
Yes, indeed. So I had a question about the nanoparticle deposition using the gas aggregation source.
Yes. Yes.
Have you guys attempted, or anyone you know of attempted to make different types of nanoparticle films using this technique? Something like semiconductors or oxide insulators rather than metals?
Yes. Yes. I didn't say much about this. Actually, in connection with photocatalysis, I mentioned the cerium oxide hybrid materials, but we have other examples. We can, I shouldn't say, one has to be careful with saying all oxides, but at least I think most common oxides we can prepare, and we can also prepare mixed oxides. In fact, we did this already in some cases. Yeah, because I showed you how we can tailor alloy composition. If we do reactive sputtering in our cluster source, we can also get mixed oxides easily. So answer is yes.
Very cool. Very cool.
Mm.
I guess that was the crux of my question, is if you can reactively sputter.
Mm.
I
Yes,
wasn't
we
sure if
can.
it introduced
Yeah,
any
actually we often
complications.
explore reactive sputtering for oxide. It gives you a much higher deposition rate also in many cases. Actually, what we also do is pulsed sputtering, pulse DC sputtering in some cases also. And so we have several options to tailor the nanostructure and properties.
Awesome. Thank you.
So Franz, I have a question about the neuromorphic side of things.
Yes.
So it seems like you're designing these synapses by using this composite structure with
Yes.
gold particles.
Yes.
How do you combine these synapses to make a neuron?
Well, we have different components. For instance, you in the human brain, you also have oscillators. Yeah. Because for spiking, you need a sequence of pulses. And for this, we also use nanoparticle-based devices in our group. And here we can use memristive devices again, these diffuse memristors. So diffuse memristors, you can charge a capacitor, and above a threshold voltage, you discharge the capacitor. And this is like, how do you call these? Sawtooth oscillators. Yeah. You can take a glow discharge lamp and a resistor and a capacitor. This would be the analogon everybody knows probably to make sawtooth pulses. And you can do the same with this diffusive memristors. And you can combine diffusive memristors and classical memristors to have such networks with spiking neurons and threshold effects. We have other members in the Collaborative Research Center who have other concepts. You can also make memristors with oxides, and instead of movement of metallic ions, you have defects, oxygen vacancies, for instance. The HP memristor, the original one by Stanley Willems, was based on oxides. There are other approaches which are pursued in Kiel on this subject. What I personally find very interesting in this field, this is unpublished recent work. You can also take a network of almost percolating nanoparticles, and then you can dynamically form links and also break up links again between those nanoparticles. And we could recently show, it's not yet published, that you get critical behavior which is similar to what is observed in the neural brain. And I see Martina here in the audience. Martina, together with Alexander Wahl, now tries to get control of such processes via plasmonic and other optical approaches.
That's fantastic. Yes, we are very interested in this field.
Yeah, that's a really exciting field. Yeah, not only pursued in Kiel, but now in Kiel, as I said, we have this collaborative research center.
Yeah. No, and there are, we are very familiar with Hermann Kolstad, his work.
Yes,
right. Electric and magnetics using for neuromorphic stuff.
Yeah.
Yeah, so I think Kiel is becoming a good destination for this
Mhm.
neuromorphic computing.
Yes. In my group, it's not the main activity, but it develops into a major activity recently because I really find it exciting.
Other questions from the folks?
May I ask a question?
Yeah, go ahead.
Yeah.
So, Franz, thank you. It was an exciting talk. Actually, it was the first time I saw such an overview talk by you, and it's really good to get such a good overview, and it's really impressive, I must say. Yeah, my question is, of course, you showed it a little bit, and it's not the main focus of your talk, but at some points you said that you also do some simulations. And I was just asking myself, which tools do you use?
Yeah.
To do simulations?
What I mentioned in this talk is density functional formalism to get quantitative information on the trap states in polymers. This is something which Stefan Schröder does. I think you are aware of the theoretical work of Benjamin Spätzler, who, this was not the contents of the talk today, but he also did some simulation in the field of magnetic materials. Yeah, we do finite element analysis, but in compared to you, who is you are a real theoretician, what we do is we buy software, we use COMSOL. So we are not we are not real theoreticians. We just apply commercial software tools. Not only, I think Sebastian also wrote his own code. Not Benjamin also wrote his own code to some extent, but mostly we are relying on commercial software. And if it gets really serious with theory, we are happy to cooperate with people like you and other theoreticians. So we are not theoreticians. Yeah. I hope I didn't make that impression. But it's amazing what you can do with these commercial tools. COMSOL, for instance, is a very good example where you can do also electromagnetic simulation. Okay, maybe you are referring to that. This was a matrix formalism, transfer matrix formalism, which was used for these to tailor the plasmonic materials in this all optical switching devices. Yeah, this is something Ron Marco Friedrich did. What I found amazing, his main subject is completely different from optics, has nothing to do with optics at all, but he got interested in such simulations. He learned how to use the software, and then he started to work on these electromagnetic simulations.
Quite impressive. Yeah.
We have time for one more question from the audience. So Franz, you showed a lot of different shapes of nanoparticles.
Yes.
And in nanoparticle, I guess shape, and in addition to the size, shape has a lot of influence on different types of application. Is there a formalism, like is there a formal theory or formal model developed on showing all kinds of shapes that can be obtained and how they influence the property?
The amount of controlling shape in vapor phase deposition is limited compared to wet chemistry. I prize the advantages of of vapor phase deposition, but when it comes to shape control, well, we have some shape control. I demonstrated that also, but in wet chemistry you have much better shape control. So in such applications where it really matters, for instance, it's not possible with our approaches to produce highly elongated nanostructures, like nano needles on, well, I showed one example where this works too, but generally it's not so easy to make nano needles or nano wires, for instance, which is much easier with wet chemical approaches. Yeah, but shape has some influence, sometimes a quite strong influence. And when it comes to plasmonic metamaterials, we cooperate with Professor Carsten Rockstuhl from KIT, who is an expert in theory in plasmonics. We have a joint project with him, and there he does calculations.
Okay. Yeah, I'm very, very fascinated because in addition to catalysis and addition to various kinds of optical application, it seems like shape can have influence on various physical properties, whether they are functional properties or magnetic properties and so on. So
yes, indeed.
it will be interesting actually to compile all these different shapes which people have synthesized, let's say below 20 or 25 nanometers.
Yes, but as I said, our approach has many advantages, but when it comes to shape, maybe the wet chemistry is preferred. But we have some shape control also.
Okay. Perfect. So I know we are 10:59. So I want to thank you so much, Franz, for taking out the time to talk to us today.
It was a pleasure. Thank you very much.
Motivating for many, many young students to try to find somehow to connect with you and work. So thanks so much. Sadie, you want to take the last minute if you have any announcements to make?
I don't have any announcements to make at this time other than we are hoping to send our new cohort this fall, well, later this fall or next spring.
Yeah. So we're aiming for January first week to send the new cohort to University of Kiel. And I have one quick announcement that on June 2 and 3, so June 2nd and 3rd, we will organize a virtual conference to celebrate international partnerships. And we are hoping that we will invite industry, academia, and government people to talk about how international collaboration is critical in advancing the science and education, and how it impacts the workforce development for future and making much more stronger for all our communities. So we hopefully invite Eckhart Quandt to invite the talk on behalf of University of Kiel on June 2nd
very
and 3rd.
good.
So if you have time, the meeting will be only in the morning because the timings are very problematic when you do international conference with all these different zones. It will be every morning from 8 to noon. So it will be basically your noon to 5 o'clock.
Yeah, will we get an announcement?
Yep. So we'll finish the website and Sadie can probably provide more updates. So she will send the invite and website link to register. But we hope you all can participate and celebrate how international collaborations are critical for advancing all our careers and making us stronger. Okay. With that, I want to end this presentation. So thanks again, Franz, and thanks all of you for joining in.
Thank you.
Thank you.
Thanks very much.
Thank you very much. Bye-bye.
Bye.
Thank you. Bye. Bye.